Hello, hello, hello. This is concrete path testing. Today we are going for the deflection of beams. We have different methods to solve the deflections of your beams. So first one is your that double integration method. Double integration method. Double integration method. So if you have a beam, general beam, there is a loading. Then we have that this is the depth of the beam. We go that at any x. We have that we take some strip. We know that some deflection would be here. That the deflection diagram, we say that the deflection diagram we draw is the elastic curve. It's the elastic curve of the neutral axis of member. It's showing the that how the that curve is formed at the neutral axis. Say this was your member at the mid. Say it represents the curve that's formed. Say the curve formed is here, this one. So this curve is representing the this displacement of these points in your y-axis. So if you take any if you go at any x, we say that the slope here is, say slope here is theta. Say the slope here is theta. We say that that theta is equals to that dy by dx. And if we want to say that that how much theta this dx contributes, we say that the small strip dx contributes small theta is contributed by a small dx. We say that this is the slope of this is the that change in slope, that's called as change in slope. So when we if we say at the if there was only UDL, the maximum deflection is at the mid, and the slope here is 0. The slope here is theta equals to 0. Then if we go at any, say if we go from the mid towards any side, either of the side, we would say that how much theta is at any place, say at any place x dash. At any place x dash there is some theta dash. That theta dash is contributed by small these theta of those differential elements, small theta of differential elements. So when we combine them, we get the value of particular theta at that location at x dash. So we have that the deflection diagram follows that some elastic curve, but we know that if there is some curve, we have a general equation that that curvature, we call it curvature of the beam, or curvature is that curvature equals to that d2y by dx2 and 1 by dy by dx, that whole square power 3 by 2. For our strength of material, we say that the elastic curve formed is that the slope of that elastic curve in strength of material, elastic curve, that is strength of material. So we say that the slope is very small. That dy by dx is very small. So we can ignore that is very small, that slope is dy by dx is very small. So we can say that d2y by that the bottom term, that's 1 plus dy by dx whole square power 3 by 2 is almost equals to 1. Then we get the relation that curvature of the beam equals to d2y by dx2. This is also we can say this is your that d We know that theta equals to dy by dx, so we can write that d theta by dx, change of slope with change in x. So we can write that equals to, we have that, we know, we derive that the curvature of the beam, is related to the bending moment at any x. So curvature of the beam is related to the bending moment at any x divided by EI. This is derived in the chapter when we study bending stresses. There we derive the flexural formula. So this one is your m by EI. So this result is going to be used in your first method, that's your double integration method. So what does double integration means? So this is your general that general equation that we got. If we say, if we integrate it once, let's say we now integrate it once, would say now we will write the equation in terms of that EI d2y by dx2 equals to your moment at any x. So this is your equation number 1. Now after that we would derive, say let's integrate the equation. We would write EI dy by dx. After integrating with respect to x, we can say it would become m. So your moment is a function of loads and your x also. It's a function of loads and x. So your moment m, so we can write mx plus some constant c1. Similarly, if you integrate second time, you can get EI y equals to mx squared by 2 plus c1x plus c2. So when we integrate the equation, we had that d2y by dx2 twice. Then we got the equation for your deflection at any. So we can get the deflection, that if you have this one is your y, this one is your x, we can get deflection at any x is your the equation that EIY equals to mx squared by 2 plus c1x plus c2. So y, we can represent y as also in terms of delta, this one, and dy by dx is also slope. So your dy by dx equals to theta. So we can get the slope and deflection at any point. So this one is your slope and this one is your deflection. So let's say let's have that. We can also that from this equation, if you say differentiate it with respect to x, we can say EI d3y by dx3 equals to dm by dx. So we know that change of that slope of the bending moment diagram is your shear force. So we can write that EI d3y by dx3 equals to your shear force. Similarly, we can integrate it differentiate it one more time. So we can get EI d4y by dx4 equals to dv by dx. That equals to your loading intensity. So we can so this result is also important. This case, this result will be used when your loading is such that, if loading is such that your moment equation, if your bending moment equation is difficult to derive, that means it takes a lot of time to get the bending moment equation at any point x. So for that, we derive that load. We derive the from this equation. Then, so from this equation, we directly use that loading that's given. Say sine loading is given. Sine function loading is a function of sine x. If the loading is function of sine x, the moment calculation becomes difficult. For that, we directly use the loading diagram intensity. Then after that, we integrate it 4 times, 1, 2, 3, 4, to get the deflection at any point x. Now we have the first question that and the main criteria for your that double integration is that the moment equation should be continuous, should be uniform in the entire beam, should be uniform. It should not change If it changes, that means your calculation becomes very, very, very long. So first problem is that you got a cantilever, and the loading is uniformly varying. So this is your loading. That, let's say the loading intensity here is W, length is L. So we have that. Let's say we want to check the moment at any x. So let's take any section that from here we say that at any x we can get the moment equation. That, say, let the intensity here is W dash, that intensity here is W dash, that equals to W intensity in length L, but for the x length we can get Wx by L. This is your intensity of the loading, and this is your x. Let's say that the shear force here is V, and the moment generated here is mx. We don't care about the shear force V. We are worried about the moment x. Let's say summation of moments at x equals to 0. Then we have the bending moment at x in the clockwise, plus area of that triangle, that 1 by 2. This is also clockwise. 1 by 2 that W into x by L into x. It acts at the x by 3, that equals to 0. So your bending moment equation becomes minus times that value. So now we have that. We can write the equation that EI d2y by dx2 equals to moment at x. So moment at x becomes equals to minus times that wx cube by 6L. So now integrate it. First time, for the first time, if we integrate it, we get that EI dy by dx, that equals to minus x to the power 4 by 24L, and plus constant C1. Then after that, if we integrate it one more time, EI delta or that y equals to minus x to the power 5 by 120 into L plus C1x plus some constant C2. Now what to do, how to deal with these constants in the differential equations? We know that we use the boundary conditions. If you say let's use the boundary conditions, that boundary conditions we are using here, boundary conditions, to get rid there's those to get rid of these constants C1 and C2, we can use the boundary conditions. Say if you are at x there is no boundary condition. We can't say what's the that slope or deflection there. But if we go to the at x equals to L, at this point fixed support, we know that deflection and slope here is 0. We can say at x equals to that L, your deflection is 0 and your theta is also 0. Let's say in the equation second equation, we can use that theta equals to 0, which implies EI theta is 0 equals to minus W. Using the value of x equals to L, we can write minus L to the power 4 by 24L plus constant C1. So your value of C1 becomes equals to your constant C1 becomes equals to WL to the power 3 by 24. Similarly, we know that at x equals to L, we can write it now that deflection at L is also 0 because the support is there, fixed support. So we can write in this equation that 0 equals to minus WL to the power 4 by 120 plus your C1 was equals to WL to the power 3 by 24 into L plus C2. So your value of C2 comes out to be equals to that minus WL to the power 30 minus WL to the power 4 by 30. So we got these two constants. Now our general equation that we want to say What is the general equation for your slope and deflection? We can write ei theta. Ei theta becomes equals to minus x to the power 4 by 24L plus some constant C1, that constant value of that WL to the power 3 by 24. Yeah, WL to the power 3 by 24. Yeah, let's have that. Similarly for the, now if you want to say what is the question was that get the maximum slope and maximum deflection. Question was get the theta max and delta max. We know that for that cantilever, the deflection would be maximum if there is loading. Deflection would be maximum at the free end, and theta is also maximum here. You can write delta equals to delta max at, you can write at x equals to 0, your theta becomes theta max, and equal then we divide that ei, so we can write that at x equals to 0, your equation becomes this part goes 0. We only are left with that wl to the power 3 by 24 ei. So this is your theta max. This is your general result, that theta max equals to that result. Then similarly we have we have the general equation for your deflection equation, that's minus wx to the power 5 divided by 120 L plus C1. That C1 value was your WL to the power 4, WL to the power 3 by 24 into your x plus that constant C2, or C2 value of minus, it was positive, I think it was minus WL to the power 4 by 30, minus WL to the power 4 by 30. Let's take minus WL to the power 4 by 30. So we have that at x equals to 0, that's your deflection is maximum, delta max. Delta max equals to that this value, first one equals this is 0 because your value of x is there, so this one is 0. Then we are left with that minus WL to the power 4 by 30 ei. That we got the theta positive and delta negative. What does that mean? We have that sign convention. If you want to say what that means, say this was your support, then because of the loading, so it deflects downwards, say this way. Loading is applied, so it deflects downwards. We want to say the theta here is uh, the curve makes it is drawn from, theta is drawn from that with respect to x. Theta is drawn from horizontal axis to the curve. Okay, right. Theta is drawn from horizontal axis to the curve. Let's say we can say that from the horizontal axis this is your theta, and from your horizontal axis this is also your theta. So your theta is clockwise here. So theta is clockwise. If theta is clockwise, it becomes positive only if you are, when you calculate the moment equation, we say that x is going from this side to this side. So for that, theta is positive in this direction, and the delta, we got that negative. We have that reference axis. We say that this is your positive x and this is your positive y. So delta is your negative, minus times that means deflection is downwards, and your theta is that positive. That means that's your clockwise moment. That's clockwise rotation. Next problem we can go with, say we got that we got a frame, we got this cantilever subjected to a moment m at the free end. So we need to get the slope and deflection. Say we cut at any x, say this is your x at any point x. We can say here the shear force is Vx and moment here is Mx. We can write that minus M plus mx equals to 0. So your moment at any x becomes equals to that value of m. So your moment is positive set sagging moment. Now let's say we have that equation that ei d2y by dx2 equals to your moment m, and similarly we can say ei dy by dx equals to mx plus c1, and we can also have that ei delta equals to mx squared by 2 plus c1x plus c2. Now we have to apply the boundary condition. Say that at x equals to that at the free and there is no boundary condition, we can say go to the point fixed support at x equals to l. We have theta equals to 0. Then we substitute that 0 equals to m into l plus c1. So your c1 equals to ml minus ml. Similarly, at x equals to l, your delta is also 0. So we can write that 0 equals to m l square by 2 plus c1 is your minus 1 ml into your x value of l. Then we have c2. Then we can get the value of c2 equals to c2 value equals to let's calculate the value of c2. Say that ml square by 2, that's 2 inverse minus 1, 2 inverse minus 1. So your value of 1 by 2, that's ml square by 2. So that means your c1 and c2 we got. So let's have that we want to get the delta max. Let's say we want to get the delta max. We can write now that we can have at x equals to 0, we have that theta max equals to, from the equation we got that ei dy by dx mx plus c1, we can write mx plus c1, that's m into x plus c1. C1 value is your minus m into l by ei. We divided this ei downward. So your equation that theta max equals to minus ml by ei. So negative means that the direction that that the theta is uh, anti-clockwise theta. So you are applying, say this is your fixed that cantilever beam. You are applying a anti-clockwise moment. Say if you are applying an anti-clockwise moment, the beam would deflect upwards. Say this one. Accordingly, we have the deflection upwards, and then the theta. This is also anti-clockwise. Theta is also rotation is also anti-clockwise. Let's have that delta max also. Can write delta max equals to, from this equation we have that delta max we can write that's first one is your 0, m into 0 square by 2 plus c1 into 0 plus c2 value is ml square by 2 divided by ei. So we can get the value of delta max equals to ml square by 2 ei. So these are your standard results. So this one and this one. So your positive value of delta means your deflection upwards. So if you have that curve, we can say it had deflected upwards. Here the theta is 0 and deflection 0. And this point, theta is from that horizontal axis. So this is your horizontal axis. From that you have to show the arrow that it's going from that horizontal axis towards that deflected curve. So your theta is anti-clockwise, that is theta is negative anti-clockwise, and your deflection is upwards, that's your positive delta. Similarly, go for the third question that now we know in this problem there is a problem that loading is that equals to w naught sine pi x by l. So for this case we have beam that we got a beam that simply supported beam and the thing is that length is only L, length of L, and we need to get the first we need to get the loading diagram, how the loading diagram would be look like, and after that we need to get the delta max and theta max. But since your loading intensity is a function of sine x, so your moment equation becomes difficult. So we can directly use that relation, that ei d4 y by dx4 equals to your loading intensity w, and still for that you have to get the loading intensity. So we have that function sine x, so your period, say period for this function, period we know that period equals to 2 pi for your function sine x. Similarly for your function that sine pi x by L, your period becomes equals to that 2 pi 2 pi 2 pi by that constant a, that value of constant a is pi by L, that's your period becomes equals to that's 2L. So if your period becomes equals to 2L, that means after 2L it would repeat, so it's your L and it's your L. So your loading intensity would be only this part. Let's say we say this is your positive, this is your negative. We can have any part of that loading. We can say this part, we can take this part, or we can take this part. And direction we can show, if we show that loading intensity is here downwards, we have to show that loading here is upwards. Now for this case, let's say the loading is downwards for this part, so your L is only occupied by this part. So your loading intensity is acting downwards, loading intensity is acting downwards. That then after that we get some reaction, we can get the reactions RA and RB. Can we get the reactions? But say let's say we got the we have the standard relation that ei d4 y by dx4 equals to your loading intensity. Let's write that equation. We say ei d4 y by dx4 equals to your loading intensity. The loading intensity, say here we kept it downwards. You could have also kept it upwards, but then after that your values would change, that the deflections. For this case we have deflection downwards, and for the next case if you said loading was upwards, so your deflection would have been upwards. So that's only the difference. So for this case we have the loading intensity negative there because it's acting downwards. We would say that we have that W naught sine pi x by L. This is your loading intensity. Now if you want to get the deflection and slope, we had to integrate it 4 times. Say now for integrating for the first time, we can say ei d3 y by dx3 equals to your shear force of say minus W naught. Your integration, you are integrating it, that means W naught cos of pi x by L into your internal, that's your pi by L by pi into L by pi plus some constant C1. Similarly, we can have another equation that ei d2y by dx2, that's your moment equation M. The value here is W naught sine pi x by L into your L square by pi square plus some constant C1 into x plus constant C2. Now from the moment equation we can have that that moment at the free end, those supports, simple supports here, moment here is 0 and moment here is also 0. So we can write the boundary condition that you can say at, say this was your any x, either from this side or either from the other side. Let's say that x was from this side. So at x equals to 0, we have that moment equals to 0. Bending moment is also 0 there. So if you write the equation that that means your 0 equals to w naught sine pi into 0 sine into 0, that the function there that becomes 0. Then after that we have c1 into 0, then after that c2, which implies c2 is also 0. Similarly at x equals to l, if you go at x equals to l, we have that m is also 0, which implies that 0 equals to w naught sine pi x value of l by l into l square by pi square. Then after that we have constant c1 into l plus c2. c2 is 0, so we can get the value of c1 equals to, say sine function is also 0, sine pi is 0, so your c1 is also 0. So we can get the values bending moment equation, that final bending moment equation, that ei d2y by dx2 equals to your moment equation m, that equals to w naught sine pi x by l and your l square by pi square. Yeah. Now we want to get the delta max and the theta max. Say so deflection would look like this one. The loading is symmetric. That means the deflection is maximum at the mid span, and theta would be maximum at this span. So if you want to calculate that, so we are going for that that let's say that we integrate it one more time. We would get ei dy by dx equals to your value of that we can say L square, that firstly we can solve w naught equation of sine pi x. If you integrate it, we get minus cos pi x by L. That means your minus, and your L, that internal, that L cube, it will become L cube by pi cube. Initially it was L square by pi square, now it would become L cube by pi cube. So plus some constant C3. Similarly, one more time, if we integrate it, we can get the ei delta equals to minus L to the power 4 by pi cube and w naught sine pi x by L plus some constant C3 into x plus C2 C4. Now let's apply the boundary conditions, that this was your support, this was your beam. So we can write that at x equals to 0, your theta would be theta max, and at x equals to L by 2, since the loading is symmetric, we can have that at x equals to L by 2, delta is delta max. We have one more condition, that say we studied that symmetric loading. If the loading is symmetric, we got that deflected shape is also symmetric. Bending moment diagram is also symmetric, and your reaction is also symmetric. So when the and delta is at the maximum, delta is maximum at this point, delta is maximum at the mid span. If the delta is maximum here, so your slope is also 0 there. This is one more critical point, that theta is 0 at mid span for symmetric loading. So in this equation, if we substitute that x equals to L by 2, at x equals to L by 2, we have theta equals to 0. We can write at x equals to L by 2, theta equals to 0 because symmetric loading. So we write that EI into 0 equals to minus L cube by pi cube W naught cos of pi into L by 2, that's cos pi by 2, that's 0 plus C3, that means C3 is also 0. Similarly, we have the deflection at x equals to 0. We have the deflection at x equals to 0 is deflection at x equals to 0 equals to 0. uh, at the supports there is no deflection, so we write that. So we have the equation that 0 equals to minus L to the power 4 by pi to the power 4, and your W naught sine pi, sine function of 0, that becomes 0 plus some C3 into C3 is also 0 plus C4. So we get the C4 also 0. So final equations of slope and deflection, we have that final equations of slope and deflection, we got that that EI dy by dx equals to L cube by pi cube, and this one is 0. Similarly, this one is 0, this one is 0. So if you want to get the delta maximum is your at, so firstly we want to say that theta maximum would be at the supports. Theta would be maximum. Say at x equals to 0, we can write at x equals to 0. So if we write that at x equals to 0, your theta is theta max. Theta max equals to when you substitute the value of x equals to 0 here, x equals to 0, we get cos pi, we got cos 0, that's 1. Then that means your value of minus L cube by pi cube into W naught divided by EI. So your theta maximum is this one. So initially we took that x from the that 0 to positive x-axis. So this was your positive x-axis, and you got a theta value of that negative. That means it's clockwise. Theta is clockwise. And similarly, we have that we want to get the delta maximum. We can write at x equals to L by 2. We have delta maximum that equals to, if we substitute value here, L by 2, that becomes equals to pi by 2 sine pi by 2. So we can get the delta maximum, that's minus L to the power 4 by pi to the power 4. That's your W naught sine pi L by 2, that's your 1. So we can write that, we can divide that EI. So we get that negative means deflection is downwards. Negative means deflection is downwards. Deflection of downwards, and it's clockwise moment. So checking the result is that W L cube by pi cube, yeah, and L4 by pi 4, yeah, correct. Now we have that we earlier said that double integration method is safe when till the moment equation is constant, uniform moment equation. So let's say you have 2 3-point loads acting on a beam, so your bending moment equation calculation would become difficult. So because bending moment equation will vary in the spans, we have to take different segments and solve individually. So for that, your differentiate that equation, that calculation becomes lengthy. So we avoid to solve that different double integration method for your beams with varying that moment equation. So if we take one that question that in which your load is also acting, say this is your load P, and you have that reaction at A, and you have that support at B. This is your support at B. This is your A, B, C. This one is your 2A. This one is your A. You got the load of P here. So if we say that the reaction here is that's so reaction here is B, the reaction here is A. If you want to say that what's the reaction value at A, we can say summation of moments at B equals to 0. We can write clockwise of A into 2A, that equals to P into, that's also, that's plus P into A equals to 0. That means A is minus P by 2. That means downwards P by 2. That means we have that downwards P by 2. Downwards P by 2. So if you write a at any x, say if you go from here, if you write at any x, so till point B there is no problem in the moment equation, because moment equation is only that function of P by 2 into x. But after that you got that support B, there is some reaction, that reaction equals to that, we can write summation of vertical forces equals to 0. We can write that P is acting downwards, that we say that equals to A plus B. Say the reaction is upwards B, then we write A P plus P equals to A, value of A is minus P by 2 plus B, that means your B value equals to 3P by 2 upwards. So then after that, when we cross the point B, there is a reaction upwards. So the effect of here is also coming, but it's only coming after after this 2A has been crossed. So this is this the effect of this is not valid in this point, in this region. So to overcome this effect, we take separately that we take separately those segments and write moment equations. We can write that writing moment equations individually, separately for your for AB and for your section BC. So we would be taking x from support A for the both sections. The reason is also that if we take for the span AB in this side and for the span CB in this side, that value of x, moment at x, there is a, we know that sign convention changes. We saw there those two questions, that if you go from this side it's positive x-axis, and if you go to this side it is negative x-axis. Deflection is positive downwards. In this case also deflection is positive down, that negative downwards, and in this case deflection is also negative downwards. But the theta is anti-clockwise here positive, here the theta is clockwise positive. So to avoid that confusion, we would be writing that moment equation in the same direction for the both segments. So for that, let's say that for this we can write for segment AB, we can write moment equation that here the reaction was actually downwards P by 2, and we have that x, and here the let's say that shear force here is V. We can write that moment at any x mx. So your moment x becomes minus times P by 2 of x. So that equals to EI d2 y by dx2. So integrating, we can integrate it. So integrating it, we can get EI dy by dx, that equals to minus P by 2 x square by 2 plus C1. Similarly, we can integrate one more time. We can get EI delta equals to minus P x cubed by 12 plus C1x plus C2. Now, if you want to apply the boundary conditions, that let's apply the boundary conditions. Say we know that at x equals to 0, we have that support. At x equals to 0, we have that support. So your at x equals to 0, your theta is 0. So we can have that if x equals to 0, theta is 0, that means your C1 is also 0. Similarly, at x equals to 0, at x equals to 2a, at x equals to 2a, we have that, or we can say at x equals to 0, we have deflection also 0. A deflection is also 0, then we have that, we have the value that C2 is also 0. Is it? By px cubed by 12, px squared by 4, px squared by 4, and px squared by 4, and x cubed by 12. So we got that C2 is 0, but condition is that we had to solve the question in such a way that we had to link the two equations for the moment equation in span AB and moment equation in span BC. We have to link we have to link them anyhow so that we can get the final delta at any point A. Say we have to get the we have to get the deflection at this point C. The question is to get the deflection at any point C. We have to see how these two moment equations are linked together. So if you want to make the deflection profile of this beam, let's say this was your say here the reaction is p by 2, here the support reaction is 3p by 2, and the load here is acting p downwards. Let's say that deflection profile would be somewhat this way, and to maintain the slope at point B, the line has to be continuous. Here the slope is same, so the line would be somewhat this way. So we have the link that theta here is same. Theta for the both spans is same because it's linking because your span AB and span BC is linked by point B, and we can have that theta at B. We have that boundary condition that theta at B is also theta at B should be same in both the spans. Theta at B should be same in both the spans. So if you want to say if you want to connect that, what is the change of what is the condition for the point for this point, what is the value of C1 and C2 at this point? If you want to calculate the points that C1 and C2 at this point, we would write that at x equals to 2a, the length was equals to 2a. If we want to say at x equals to 2a and at x equals to 2a, we have theta equals to, we can write that theta equals to we can write theta equals to uh, so we don't know the value of theta. We can solve that. We can write that ei theta equals to minus p. uh, the value of x was your 2a, that's your 2a whole square by 4 plus c1. And for the at x equals to a, we want to say delta is also 0. At x equals to 2a, delta is 0. Deflection at 2a equals to 0. Let's say that ei delta equals to minus p, but the delta here is 0, so we can write minus p into 2a cubed by 12 plus c1 into x was your 2a plus c2. And from this condition we can say you're having two unknowns. To make that unknowns that are gone, we can go for the boundary conditions at x equals to 0. If you want to go for the uh, boundary conditions at x equals to 0, we can write there is also that here the deflection is also 0, the delta here is 0. If you substitute here that yeah, initially I wrote that equation that theta was 0 at x equals to 0. That was not true because I wrote that initially. That was the confusing part, that I wrote initially that at x equals to 0 theta was 0, but it was not true. At x equals to 0 there is some deflection. Let's say I have shown you the deflected curve. At x equals to 0 there is no deflection, there is theta, but deflection here is 0. Similarly here at support B there is some theta that's not 0, but the deflection here is 0. So if you want to say uh, if you want to write that boundary conditions, we can write boundary conditions at x equals to 0, and at x equals to 2a we have deflection equals to 0. If you're using that deflection equals to 0, we can get the value that we can say, so for at x equals to 2a, we got that relation in terms of c1 and c2. Similarly, we can write at x equals to 0, where your deflection is also 0. So for so we can write that 0 equals to minus p that we have that this one equation that ei delta, we have that delta equals to 0 at x equals to 0. Then after that we have minus p into 0 cube by 12 plus your c1 into 0 plus c2. That means your c2 is 0, that we earlier calculated when we applied the boundary conditions at x equals to 0. So your c2 becomes 0, your c2 becomes equals to 0. Now if your c2 becomes equals to 0, your equation becomes that we can write the general equations now in terms of c1. Now we have the equation that ei delta equals to minus p x cubed by 12 plus c1 into your value of x, okay. Similarly, we have that equation for slope ei theta that equals to minus px square by 4 plus constant c1. This c1 was not 0 because theta was not 0. How can c1 be 0? So that was wrong that at that time when we substituted that theta is 0 at x equals to 0. Now now we have to get the value of c1. We have to get the value of c1 anyhow. If we write that, if we write now, we have this equation that at x equals to a, we have that delta equals to 0. Since we used one more once we used that at x equals to 0, your delta was 0. From that we got c2 equals to 0, and c1 was a function of x, so c1 is still unknown. So for that, to get the value of c1, we use the boundary condition that at x equals to 2a, your delta was 0. So if you say that your delta was 0, that means your equation becomes minus p 2a cubed, that's 8a cubed by 12 plus c1 into 2a equals to 0, which implies that c1 becomes equals to p by 3, pa square by 3. Now we got the boundary conditions, we got the value of c1 and c2. Now if you want to make that slope equation now, if you want to write the slope equation now, that theta, you can write the slope equation now, modified slope equation, that ei theta equals to minus p x square by 4 plus constant p, that constant c1, that's equals to this. So this is your general equation for your span AB. For AB, this was your general equation for the theta. So we have that theta here should be same, theta in this span and theta in this span should be same. So to write the equation, that now we had to write the equation for your span BC now. See how lengthy the calculation become if the moment equation changes. So you have to solve and calculation becomes very lengthy if the bending moment equation changes. Now we have to write that equation for that CB we got the value of B equals to 3p by 2. So if you are solving now, we can write that let's have that equation at any x mx. We can write here the shear force is V and moment here is mx. Now we can write that p by 2 minus p by 2 because it's anti-clockwise into x. Then after that we have we have that the reaction here is 3p by 2 upwards, so we have clockwise 3p by 2 into, it's acting in the length that x minus 2a, then we have that moment anti-clockwise moment of mx equals to 0. That means your moment x becomes this one. So we have moment at any x equals to this, we can write it equals to ei d2y by dx2. Now similarly we have that ei dy by dx equals to, after integrating it, we get the value that minus p x squared by 2, and it becomes 4. Then we have that 3px. We can simplify the equation. It becomes equals to initially that uh, p into x minus 3a, x minus 2a, p into x minus 3a, 2a, 3a, 2a. Yeah. If you simplify this equation, it would become that p by 2 x minus p by 2 x plus 3 by 2 px, and plus minus that 3 by 2 into 2a into p. So your equation becomes finally that p into x minus 3a. Yeah, you have to integrate it. So your equation becomes p into x minus 3a. Now you have to integrate it. So after integrating, we get the value of x squared by 2 and 3a into x plus some constant c1. Similarly, we have that ei delta equals to p into x cubed by 6 minus 3a x squared by 2 plus some constant c1 into x plus c2. Now if you want to apply the boundary conditions, we can say we can write that for the case 1, for this case we have that theta, we know that theta at this point, at point B, at support B, theta should be same as we got in the initial case. So let's say that this c1 equals to, we write it as c3, and this one as c4, this one as c3, c4. So get the value of c3, we can write that at x equals to 2a, your slope is also same as we got in the first case. So we can write, this is the main critical step here, that at x equals to 2a, your theta becomes equals to, we can write that then equation that theta equals to in this if you substitute value of x equals to 2a in this equation, we can get that p into value of x squared, that is 2a squared, that is 4a squared by 2 minus 3a into x value of 2a plus some constant c3 divided by ei. We can write here it ei. So now we have the condition that the theta here, we have the condition that theta at b in AB equals to theta at B in BC. So to substituting the values and combining them, we can get the value, say ei theta equals to value of that p into 4a squared by 2, that's 2a square minus 6a square plus c3, and here you have to substitute value of x equals to 2a. Then after substituting the value of x equals to 2a, it becomes 4a square, and then you calculate it, you get the value of c3 equals to 10 by 3 pa square, 10 by 3 pa square. So if we substitute the value of c3 in your delta equation for the member BC, this equation, if we substitute value of c3 here, we can write that now we can write that at the final question, which was that get the deflection at C. So if you want to get the deflection at C, we can write at x equals to 3a, delta becomes delta C. So we can calculate that at x equals to 3a, your delta c becomes equals to ei into delta c, then p into your value of x cube. That's value of x cube becomes equals to that 3a cube, 3a whole cube. We can write p into 3a whole cube, then divided by 6 minus 3a x square. Then after that we have one more c3 into x. The value of c3 here is that value of c3 is 10 by 3 pa square, and the value of x here is 3a, and we can get the value of c4, and the c4 value comes out to be equals to first we have to get the value of c4. So we can say let's say this was your delta at c, but before that we don't know the value of c4. We don't know the value of c4. We have to apply one more boundary condition, that we can write at, let's say, at x equals to 2a. At x equals to 2a, we can get the value. We can, at x equals to 2a, we have that delta is 0 because the support is there. At x equals to 2a, your delta is 0, and you can get the value of c4. That comes out to be equals to minus 2pa cube. Then finally substitute the value of c4 here, minus 2pa cube. Then you can get the value of delta at c equals to minus 7 by 6 pa square upon ei. And the deflected shape would look like that. Here it was support A and support B. You apply load of P here, so it will deflect downwards. This is your delta C. There is also some theta here, theta C. And then to maintain the slope in the left and slope in the right should be same. Then after that you join the two. So this is your deflected shape. Here theta naught equals to 0, but here theta b left equals to theta b right, and this was your critical condition for this question. And here delta is 0, and here delta c. So this question became very lengthy by using the double integration method. Now a modification of this method came, and that method we call as Macaulay's method. So we can write that Macaulay's method. This is, we can say, this is an advancement. It's advancement in your double integration method. So we can have moment equation for entire. We can have moment equation varying. Moment equation is same. Moment equation, we write only one equation such that the effect of all those loads is included in that equation. We can say it's valid for all. Also it's valid also if that moment equation changes. But the moment equation we are writing same, then how moment equation, if the moment equation changes, but we are writing only one equation for the moment. Actually we are say we have say we have that this is your say configuration of that loading and beam. Here A, here B, here P and P. Say this is at distance A from A, and this is at distance B from A, and this is at distance C from A. We can have that we say that right here the condition is that we write bending moment equation for the last segment. If you write the bending moment equation for the last segment, say your x varies from A to point D. If you cut section just before D, dx before D, you can say cut dx before D. Then after that we write moment equation. Say here the moment here is mx. We can get the value of, say here the reaction is A. We can say moment summation of moments at x equals to 0. We can write A into your value of C. The value here is x because you are cutting the section at x, so we can write A into x, then minus P into x minus A, because this length x minus A. Then similarly minus P x minus B. Then after that you have moment x moment mx, bending moment mx, that's anti-clockwise direction, so we can write mx. So your equation becomes minus that, so we got the equation, but how it's valid, but the terms that this value and this value, say this value is not valid for this part, and this term is also not valid in this part. But when after you cross the point P, after you cover this point P, the equation that P x minus a is valid in this part, but it's not valid. This part is not valid in here. Similarly, when you go for the last segment, the all three terms are valid. So to to make the things clear, we apply that we apply that Macaulay's signs. We write that we apply Macaulay's signs. We write ax minus b x minus a minus b x minus b. Then after that we apply signs that we we use oblique signs after these terms. So this depends, this oblique, the oblique we applied, that oblique applied, we say that it represents that whether 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 this term whether whether the term is valid or not. Say say uh, say the condition that if the value of this term, internal term, that x minus a x minus b, if 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 it comes up to be negative, if it is negative, if negative, we have to ignore the term. We have to ignore this entire term. So if it is negative, we have to ignore. Negative means, let's say, we were calculating for this span. Negative means, that means your x was only this part. X was only that x was less than a. If it is less than a, that means small, that value of x minus a, that's negative. That means this part is not valid for span this one, and this one is also not valid because it's negative value. So ultimately this effector and this effector got cancelled for your span AB, and after that the effector here would be there, but the effect of this one would not be here, because value of x would be somewhere here, but your b is this much, so your value of x minus b is negative, so we have to ignore this term also. So this is how this approach looks like. So we have the question, the question we solved in the double integration last question. We'll be solving the same question by this method now. Let's say this was your point load P, and here the reaction was, we know reaction here, and this was your support B. The length was 2a and length was a. Let's say that the reaction we got as p by 2 downwards, and here the reaction was 3p by 2 upwards. So if you want to write that moment equation for the entire section by double integration, we have to get the delta at c. We can write, this is your x just before the end segment. This is your section x. We can write here the, let's say here the these what you call a shear force here is v, and moment here is mx. We can write that p by 2 anti-clockwise into x. Then after that we have 3p by 2 clockwise, but it acts after x minus 2a. It acts after that. It's valid for this one, that after 2a has been crossed, so it's valid for x minus 2a. So after that we have moment equation clockwise, that mx, then we can equate it with mx. Finally we got the equation of moment equation. We can write that, now we have that ei d2y by dx2, that equals to moment x, m at x. So we can write that minus p by 2 into x plus 3p by 2 into x minus 2a. Now we have to apply the oblique signs also, that after this one you have to apply the oblique sign. Now we have to integrate it, and ei dy by dx, that equals to minus p by 2 into x. And the constant terms we got, that c1 and c2. This is also a point you have to remember, that this constant c1 c2 to be added in the first term, to be add it in the first term, add it in first term, because your first term is always valid for any section, for any segment. Your first term is valid for all the sections, all those sections you cut. This condition is valid for all the cases. So we have to write the c1 and c2 in the first that term. So we can write c1. Then after that we have this oblique. Then after that we have positive sign. So we have to integrate the term, that's the function of x. And here the critical case is that we don't have to integrate it. We don't have to integrate it in this way, that we don't have to integrate it x minus 2a, that equals to, if we integrate it dx, we say that it is x squared by 2 minus 2a square 2ax. It's not you don't have to integrate it this way. This term is a valid only after that, after point b. So these things won't make any sense for this condition, because we have to make sure that this term is valid only after the point that it has crossed 2a. So we have to keep it as it is. So when we integrate it, the correct way for this one is to keep it that this is only a whole function of x. So we can write this is a function of x. So we can write that after integrating it, we can get value of x minus 2a whole square, and the power is divided by 2, that divided by 2. It's not this way. You have to also write it side at the side. This is not correct here. Now we have also the ei. After integrating it one more time, we have ei delta equals to minus b by 2 x square by 2 plus, yeah, actually the moment equation was that minus b by 2x. So it would have become that x square by 2, and here it would have been x cubed by 6, x cubed by 12, x cubed by 12, x cubed by 12. So finally we got minus b x cubed by 12 plus c1x and some constant c2. Then we write that 3p by 4. Then we have that x minus 2a. Now the power will increase by 1, so we can write 3 divided by 3. Now we got that slope and deflection equations. Now we have to apply the boundary conditions, that at if we say at x equals to 0, at x equals to 0 we have delta equals to 0. If you write that at x equals to 0, delta is 0. At x equals to 0, delta is 0. So that means it becomes 0 plus c2, and this term, it's not valid because you are writing 0 minus 2a, that's negative. You can say it's ignored. We write it as ignored. This term is not valid, so your c2 comes out to be 0. Similarly, we can have that at x equals to 2a, we have delta also 0. So if we say also that at x equals to 2a, delta is 0, because in terms of theta, we don't know the value of theta at any point. Say at this point we don't know the value of theta, and this point we don't know the value of theta, and at this point we don't know the value of theta. We only know that delta here is 0 and delta here is 0. So we have to apply the boundary conditions in terms of delta only. So at x equals to 2a, delta is 0. So if we substitute the value, we can say in this equation that ei into 0 equals to minus b into x cubed, that is 2a cubed by 12 plus constant c1 into 2a plus 0. Then after that we have 3p by 4. Then after that we have to use the value of x equals to 2a. That means 2a minus 2a by 3. That comes out to be 0. So value of c1 that we got as we can get value of c1, and that comes out to be equals to pa square by 3. Once you got the value of c1 equals to pa square by 3, we can say that your delta, we need to get the delta at point c. This is your point c. So once we got the conditions, we can get easily that delta at C equals to this equation at delta at 3a. We can write, yeah. Now the question was that at x equals to 3a, we have to get the delta value of C equals. We can write ei delta C. Ei delta C equals to minus p x cube is your 3a cube by 12 plus constant C1. The value of C1 we got as PA square by 3. PA square by 3. And we got the value of C1 equals to PA square by 3. Then after that we had to multiply it with x. Value of x comes out to be equals to 3a. Then after that we have to see whether the term is valid. Now this one we have to let's say we apply oblique also. Then after that we apply plus. The sign was 3p by 4, 3p by 4. So we can write 3p by 4. Value of x, we have to substitute value of x equals to 3a minus 2a, and divided by 3. So value of, so here we have to apply the x equals to 3a. So your term is valid because it's the last term, and we have to derive we have our value of x is greater than 2a, so it's valid here. So we can write that. So finally we can get the value of delta C. So this oblique we can remove now because your term is valid. That means you can add this one also in the total terms. So we can get the value of delta C, that equals to minus PA cube by EI, minus PA cube by EI. You can verify the value of the delta at that point. You have to verify that value. Similarly, let's say now we have beam that at a from that support we have that point load on, and after that we have a concentrated moment at point B from A. Then we have the length L. If you want to write if you want to solve this question from the that Macaulay's method, you have to make the one single moment equation at x just before end. Say here the shear force is V and moment here is mx. You can write equation that, say the reaction here is upwards A. We can write A into x, then minus B acts at x minus A. Then after that we have a moment, clockwise moment of plus m. But the moment here is, the thing about the moment is that where the moment is, we have to show where the moment is acting. We can write moment is acting at x minus A, at x minus B. Moment is acting at x minus B. But the thing is, value of A into x is your kilonewton meter, but moment is already kilonewton meter. So we have to show that that moment is acting at x minus B, but the unit here is kilonewton meter into meter. So we have to raise the power by 0. If you use the power 0, that means m to the power 0. That means okay, no problem for the equation. Then after that we have that mx. We have that mx anti-clockwise. We can write that finally mx equals to this equation. So we can write moment at x equals to ei d2y by dx2 equals to ax minus bx minus a. Then after that we have plus mx minus b. Then we can apply oblique signs. So this one we have to apply power 0. So then after that we can get the deflection and slope at particular points. Let's say we have a question that we have a simply support beam. We have concentrated moment of m at L by 2 from both sides. Say this is your point B, A support B and C. We can get the value of reactions. Here the reaction would be downwards m by L. Here the reaction would be upwards m by L. by summation Fy equals to 0 and summation moments at C equals to 0. We can write A into, we can write, let's say, summation of moments at A equals to 0. We can write that 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 C into L, C into L equals to C into L and equals to M, then C equals to M by L. Similarly, if C is this one, A is minus M by L. So we got we have to get the single moment equation. Say this is your value of x just before C. We can write here the shear force is B x and moment here is mx. We can write that minus M by L, because your A reaction is downwards, so anti-clockwise moment of M by L into x. Then after that, we have to show where the concentrated moment is also acting. So plus M x minus L by 2 power 0. It shows that the moment, concentrated moment M is acting at L by 2 from A, so we have to raise the power to 0. Then after that we have moment mx anti-clock. So finally we have moment equation, this one, that equals to, we can write then ei d2y by dx2, that equals to that minus M by L into x plus M x minus L by 2 power 0. So applying oblique sign, that now we have the equation that we would integrate it one more time, first time, that then we get ei dy by dx, that equals to minus M by L, the x squared by 2 plus constant c1. Then after that we have M x minus L by 2 power 1 divided by 1. Similarly, we have that ei delta equals to minus M x cube by 6L plus c1x plus c2. Then we have that M x minus L by 2 squared by 2. Then we have to apply the boundary conditions. Let's apply the boundary conditions. That we know that at x equals to 0, your delta is 0. We don't know the value of theta. Theta could be anything, that we don't know the value of theta at A. So we can say at x equals to 0, delta is 0. Then substituting the value of delta in this equation, we can say, so which implies that 0 equals to 0 plus c1 into 0 plus c2. Then after that, this condition, that 0 minus L by 2, that 0 minus L by 2, 0 minus L by 2, it's not valid. So we can say ignored. We can ignore this term also. That means c2 equals to 0. Then after that we have one more condition. At x equals to L, we have also delta 0. At x equals to L, we have delta 0, because theta, we don't know the theta, where the theta is, how much theta would be there at any point. So if you write that delta is 0 at theta, delta is 0 at point C, that's x equals to L, delta is 0. So if you write that delta is 0 at x equals to 0, x equals to L, you can write minus M L cubed by 6L plus C1 into L plus 0. Then we have to see whether this term is valid or not. We write M by 2. Your value of x equals to L, yeah, it's valid, because L minus L by 2 is positive value, so it's valid. Then it has a square, yeah, square. So if you solve that, now we can remove this term also. We can write positive plus, so this is valid. So we can get the value of c1, that comes out to be equals to c1 equals to minus 2 m or something, minus 2. Let's solve. Let's calculate that. We can say minus m L cube minus ml cube. Let's take minus ml cube common. We can get the value of 1 by 6, then plus 1 by 2 into your L minus L by 2 is L by 2, so we can get the value of 1 by 4. So we can say 8 inverse plus 6 inverse. Yeah, yeah, the value comes out to be equals to ml square by 6. Then we have ml minus l by 2. So 1 is your negative. Say this was your negative. Let's say this was your negative. So we have to write minus times 6 inverse. So value of that c comes out to be equals to value of c comes out to be equals to m m m m l, because c1 is also having that value of l also, and l was also there at the down point. So we can write. So finally we get the value that if you solve it, if you calculate it, we get the value at ml by 24. ml by 24. C1 would come out to be equals to ml by 24. Once you got the value of C1 equals to ml by 24, that say your deflection equation becomes that. Finally, your deflection equation would become say your C2 was 0. Your C2 was 0. We can remove this part. Your C1 becomes that we can write C1 into x plus C1 into x. C1 was your ml by 2, ml by 24 into x, and similarly here it was ml by 24. Now we have to get the values of moments and that. Yeah, we have to get the moment. Yeah, theta here. Say because of this moment, there would be some say upward displacement of this part, and to maintain the slope here would be downward moment of this part. It would be some theta a. Here would be theta c, and here it is theta b. We need to get the value of theta a, theta b, and theta c. So let's say for the theta a we have x equals to 0. Let's say you want to get the value of theta a, we can write ei theta a. We can write at x equals to 0. We write at x equals to 0. We have ei theta a equals to 0 plus ml by 24. Then after that, the term that comes out to be negative, because that 0 minus l by 2, that's negative. We have to ignore that. So your theta a, that equals to ml by 24 ei. One more standard that result, ml by 24 ei. Similarly, at x equals to l, your moment with also that theta would be theta c. That theta would be theta c, but that is also equals to theta a, because by symmetry we can have theta both theta c, because moment is acting at midspan. We can have the same value of theta. So if you substitute value here, that we can write ei theta c. Let's say at x equals to l, we would say what's the value of theta c. Ei theta c equals to minus m l square by 2l, then plus ml by 24. And we have to see whether the last term is valid or not. Yeah, if your x is value is l, that means your term is also valid. So we can write that term also, m l minus l by 2 power 1. So we can write that 2 inverse plus 24 inverse minus 2 inverse. Yeah, we got the value as ml by 24 ei theta c. Both are positive. Both values we got positive. Positive means that let's say your x was from here, from positive x-axis, that left to right. This was your value of x. Then after that, for this condition we have anti-clockwise moment positive, yeah, we can say that not anti-clockwise moment positive. We say that theta anti-clockwise is positive. If the theta is clockwise, yeah, the anti-clockwise theta is positive. So if we see here at point A, your from the x-axis your theta is anti-clockwise, that is positive. And for the point C, from the x-axis your theta is anti-clockwise, that is theta is positive. So now we have to get the value of theta b, that means at x equals to L by 2 we need to get the value of theta c. So finally we can say here, substituting the value of, we can write that at x equals to L by 2, get the value of theta c. Let's say that's this is theta b. That means your value of x equals to L by 2, that means L square by 4, and similarly c1 is constant. We have to see whether this term is valid, that means L by 2 minus L by 2, that's 0. L by 2 minus L by 2, it is 0. So we get the value of theta c, theta b equals to that ml by minus, that's ml minus 1 by 8 plus 1 by 24 and divided by ei. So 24 inverse minus 8 inverse, wl square by 12, that's minus wl square by 12. We got a value of negative value of minus wl square by 12. That means negative means it should be clockwise, minus wl square by 12. So at the point B, if you see that from the x-axis, so your theta is clockwise, or in this span also your theta is clockwise, negative. So but the thing is, now we can get the delta also at any point. Say if I to say what's the value of delta at L by 2, what's the value of delta at L by 2, you can get the value of that at because it seems that delta is maximum somewhere near L by 2. We don't know value where exactly L by 2 that maximum delta would be. If you want to say what is the value of delta at L by 2, we can calculate that delta at L by 2 from this equation, that at x equals to L by 2, at x equals to L by 4, actually at L by 4 we can get the value of delta at L by 4 ei, that equals to minus m L by 4 cube by 6L plus ml L by 4 24, and this is not valid because your value of L by 4 minus L by 2 is negative, so we have to ignore that part. So finally we get the value of delta L by 4, that equals to, that comes out to be equals to ml square by 128 ei, positive means upwards. Similarly we can get the value of delta at 3L by 4, that means at the span, that third at this part we can get the value of delta c, that is negative, that means which is downwards. We can get the value that at x equals to 3L by 4, you have to substitute the value of x equals to 3L by 4 in this equation. You can get the value of delta at 3L by 4, that comes out to be equals to minus ml square by 32 ei. Yeah, we have now one more problem, that we have one more problem that's saying that that you got a propped cantilever with a point load of 6 kilonewton at 1 meter from B, and the length here is 2b. So we have to get the shear force, we have to get the reaction at B, and we have to get the theta at B. If you see that, if you see the deflected shape of this curve of this beam, it would be somewhat this way. At point B, we have that support. There would be some reaction B. So here delta would be 0. We have that compatibility condition, that delta at B equals to 0. This we already know. So this is your known displacement. From the known displacement, you can get the unknown force, that unknown reaction B. So here there is some theta. So we need to get the theta B, and we know that at fixed support theta is 0. theta is 0 and delta is also 0. So if you write the compatibility that delta at b should be 0, we have to make sure that delta at b equals to 0. Then from that we can get the value of that reaction b. Let's say uh, if you want to start from this side also, you can go with that also, but uh, better is to go with from this side, because your calculation will be erased, because you don't have to get the value of reactions at a, because you have to get the reaction ma and your reaction ra. So we can take the section from this side and go up to the point just before a. So this is your x. We can write here the shear force is Vx. Moment here is Mx. We can write that, say Mx is clockwise positive. We can write Mx, and your reaction B, we assume that it is upwards. So it's anti-clockwise B into x, and clockwise of 6. And 6 acts for this length, that total was x, but it acts after that 1 meter. After this 1 meter has crossed, so your equation becomes that bending moment equation, that mx equals to bx plus bx minus 6 6x minus 1. Yeah, now we have that equals to, we know that equals to ei d2y by dx2. So now we have to apply the oblique signs also. Let's say this is your oblique sign. Bx is valid. Say this b into x is valid for the all those spans. Say this was your span AB, this was your span BC, this is valid for the all spans. So this is your first term. Then after that you have next term, that minus 6x minus 1. Now if we integrate it once with respect to x, we can get ei dy by dx, that equals to bx squared by 2 plus some constant c1. Then after that 6, then x minus 1 whole square by 2. So after that we have to integrate it one more time. We can get ei delta, that equals to bx cubed by 6 plus c1 x plus c2. Then we have that minus 3 x minus 1 whole cube by 3. So now we have to apply the boundary conditions. If we apply the boundary conditions, we can say that at x equals to 0, we know that here the delta should be 0. Delta is 0. If we substitute it here, we can get that 0 equals to b into 0, that means 0 plus 0 plus c2, and this part is ignored because that 0 minus 1 is negative. We have to ignore. So we can write that c2 becomes 0. Now for the c1, how can we get the c1? But it's in terms of that theta. Yeah, if we say that at x equals to, let's say at x equals to length of 3 meter, because total length is 3 meter. So we can write at x equals to L, that equals to 3 meter. We have theta is 0 because that support is fixed. So if we substitute here, we can write that 0 equals to b into x squared, that is 3 squared by 2 plus c1, and we have to see whether this term is valid or not. So for that we write that minus 3. So 3 minus 1, that's positive. That 3 minus 1 is positive, that means it's valid. So we can remove that oblique sign. So we can write minus 3 into 3 minus 1 whole square. So we get the value that we have two unknowns here. So this one is your equation 1. So we can write that 0 equals to 3 is a 9 by 2. So 9 by 2 of b plus c1, and minus 4 12, that's 12. So we got one equation. One more equation we can get between c1 and b, such that we can get the two equations and two unknowns. We want to see whether there is one more equation anywhere. So here we got the theta where that theta here is 0. If you want to say delta is also 0 here, we can write at x equals to 3 meter, delta is also 0. So if you substitute the value of delta equals to 0, if you want to say value of delta is also 0 here, at x equals to 3, delta is 0. That means at x equals to 3, delta is 0. So we write b into 3 cubed by 6 plus c1 into 3 plus c2 was 0. And we have to see whether this term is valid. Minus 3 by 3. X minus 1 is 3 minus 1 whole cube. So this is valid, so we can get the value of that equation in terms of b and c. So we have two equations in b and c, b and c1. So we can get the value of b and we can get the value of c1. So b1 and c, with that we calculated, and we get the value of c1, that is equals to minus 2, and value of b, reaction b comes out to be equals to 3.11 kilonewton. Once we got these two values, so this was the question that get the reaction b. So we got the reaction b. Now we have to get the theta b. Now theta b is at x equals to 0. So we can write at x equals to 0, we have theta b. So at x equals to 0, we have theta b. Theta b into ei. Theta b into ei. Now we have to write x equals to 0. And c1, we got the value of c1. c1 was equals to minus 2. So we got the value of c1 also. Now we have to see whether this is the valid. See, this is not valid because 0 minus 1, that's negative. So we have to ignore this part. So finally we got that theta b equals to minus 2 by ei. Minus 2 means your reference was in 0 to x axis. That means right to left. That's negative. And for that we have clockwise theta positive and anti-clockwise negative. If you want to see what is the direction of the theta here is anti-clockwise. That means negative. Theta is anti-clockwise. Theta is anti-clockwise negative. So this was the question. Now we have one more. Say this was your one more question that L by 2, L by 2, L by 2. Okay. This is your support A. Here the point is B, point is C, and point is D. Here the load is P kilonewton, and here is 2P. So we had to get the say the deflection profile would be somewhere this one. Here we have theta. We have to get the value of theta A, and we have to get the value of delta at B. We have to get the value of delta at B. So we can write that. So we can get the reaction 1. For the Macaulay's method, we have to cut the section and write the bending moment equation for the entire last segment. Before that, we have to get the reaction at A. We can get the reaction at A. Now we can solve that reaction at A. That comes out to be equals to 5 by 3 of P. 5 by 3 of P. 5 by 3 of P. Then you write the equation that 5 by 3 of P into x. Then after that you have minus 2P into x minus L by 2. Then after that you have that minus P into x minus L. Then you have equals to mx. Then this is the summation mx equals to 0. So after that you can write ei d2y by dx2 equals to m by that equals to mx. That equals to 5 by 3 px. Then after that you have to apply these oblique signs, minus 2p x minus L by 2, then oblique sign minus p x minus L. So then after that we have to integrate it. Ei dy by dx, that's 5 by 3 p x square by 2 plus c1 minus 2p x minus l by 2 whole square by 2, then minus p x minus l whole square by 2. Then after that we have ei delta p by 3p x power 3 by 6 plus c1 x plus c2. Then we have that minus p x minus l by 2 whole cube by 3. Then we have minus p x minus l cube by 6. So we got these equations. Now we have to apply the boundary conditions that we have to apply the boundary conditions that if we say that at x equals to 0, you have delta 0. If you apply that here, delta is 0, that means this is 0, that means this is 0 plus c2, and this is ignored and this is ignored. So we got the value of c2, that is 0. So c2 becomes 0. Now we have one more boundary condition that if you go to the point D, that's at x equals to 3l by 2, your delta is also 0. So if you substitute here that delta is 0 at x equals to 3l by 2, you can get that p by 5 by 3 p 3l by 2 whole cube by 6 plus c1 into 3l by 2. Then after that, this term is also valid and this term is also valid because the point is at the value of x is greater, that is 3l by 2, that's greater than l by 2, and that's also greater than l. So we can also use those terms. Then plus we have to write that minus p into 3l by 2 minus l by 2 whole cube divided by 3 plus minus p by 6 3l by 2 minus l whole cube. Yeah, after calculating the values, you can get c1, that's equals to c1 value comes out to be equals to minus 7 by 18 pl square. So once you got the value of c1, you have to calculate the value of theta at a. So you can say at x equals to 0. Now we can write that at x equals to 0, you have theta a ei in this equation. That equals to value of x is 0. That means c 0 plus c1 is minus 7 by 18 pl square. Then after that, these terms will be ignored because value of 0 minus some term that's negative, so we have to ignore. So finally we got the value of theta a, that is equals to minus 7 by 18 pl square upon ei. This is your theta a. Similarly, negative means your x was from left to right. For that anti-clockwise is positive. If your theta is negative, that means it is clockwise. Theta is clockwise. If you want to see here, your theta was clockwise, so your theta is negative. That means that negative means that theta is clockwise at point A. Now you need to get the delta at B. Means at x equals to L by 2, you have to get the value of delta B. So for that, you have to get the value of delta B. You can substitute value of here. You can write ei delta B equals to p by 5 by 3, and substitute the value of x equals to L by 2 in this equation. So we can write ei delta B, that equals to 5 by 3 p into 3L by 2 whole cube divided by 6 plus constant value of c1. C1 came out to be equals to minus 7 by 18 pl square, and you have to multiply it with x. Value of x we use that L by 2. Then after that, your term that L by 2 minus L by 2 becomes 0. After that you have 0, and after that you have L by 2 minus L, that is ignored, negative. So finally you get delta B equals to minus 23 upon 144 pl cube by ei. Negative means deflection is downwards. If you want to say that what's the delta max, if you want to say what's the delta max, say if you want to say what's the delta max, based on the loadings, we can say that delta is increasing here from 0 to some value of delta at b, and here it's also increasing to delta c. But based on, because of these loadings, we can think that delta would be somewhere maximum in this span. Say in this span delta would be maximum. In this range there would be delta, possibility of delta is maximum here in this span bc. If you want to say for the span bc, what should be the value of x for which delta is maximum. But one condition is that we say that the in the curve, in any curve where the sagging is more, that's where the delta is maximum. At that point, if you draw a tangent, your theta is 0. It's the condition that at delta, if delta is maximum anywhere, at that point on the curve, theta is 0. So if we say that at any x, theta is 0, if we substitute that this is 0 at any value of x, but for that we have to say that there is a possibility that the value of x would be in the range, in this span, say value of x would be from L by 2, x would be from L by 2 to L. There is no possibility that that x would be in this part. So if we say that theta should be somewhere 0, here. So for that we don't have to we have to ignore this part, that moment equation of this part. So if you write that theta is 0 here, then we say okay, this part is okay, c1 is also okay, but x is also okay, but this part we can't write, we have to ignore this part. If you ignore this part, then you get equation that equation of x square. We get the equation that if you remove this part, well, say we are removing the part, this one. So if you are saying that x is 0, that theta is 0 in at any x, so this is at any x, so we can write that theta is 0 at any x. We can write that 5 by 3 p x square by 2. So finally we can write 5 by 6 of x square, then plus your c1 value was 7 by 18 pl square. Then after that you had minus 2p, that you have p into x minus L by 2. Then you had this, you had to solve this quadratic, and that's this square equation. We have to say this is x square plus L square by 4 minus 2 xl. Then this one. So then after that we can say p is common here. We can ignore the p. And we get the equation that in terms of x and L, we can get the value of x that comes out to be equals to 0.7270 L. That means after that L by 2 has crossed, there is point at this 0.7 at 0.707 L. Say this is your length L. At this point delta is maximum. So if you want to say what is the value of delta maximum, we say that we can write that at x equals to 0.770, and that 727 that we got 7270 times of L, we have delta maximum into EI equals to that equation, that delta equation. In that part we have to ignore the last term because that was not included in the calculation of x. Third part you have to ignore. When you ignore the third part, then you substitute the value of x, then you can get the delta maximum. That would be minus 0.1932 PL cube divided by EI. So this was the case for Macaulay's. Now if you want to use Macaulay's method for the loading such that it is UDL, or it's uniformly varying load, for that Macaulay says that Macaulay said that let's say you are having a load, so, in this fashion. Say this was at point A, and this was your point B, and this was your length L. Macaulay says that that cut the section just before the end span. Here the shear is Vx, and moment is Mx. Uh, now we say that Macaulay says for the UDL and UVL, you have to do one thing. You modify it till you reach end span. Because if you say that moment equation here is moment equation becomes that here the reaction is A. So reaction A becomes that A into X. So this is your X. At this point, this is your X. We can write that AX minus B into X minus A. Then after that you have a loading of that loading W for length B. Then we can write W into B, and it acts at, see, your value of X is here. So your value is in that going at any point. You don't know the value where up to which point the value of loading intensity is that. If you say that I am here, that X is only here, the effect of W into X minus A, we don't know where the W into X minus A is acting. And if you cross that W, if you cross that this line point B, after that your loading is not continuous, but your equation would be there, that because you say you can write that for this span you have X minus B whole square by 2. You can write this way. Then after that you say where is the loading acting, why at what point loading is acting. So you want to say here, but the loading is not in this part, but you are writing equation that X is greater than B. That means it's positive. We have to get the value of this one, but it's not true because your loading is not there. So to make this confusion clear, we say that make the loading continuous. If you say we want to make the loading continuous, that if you want to say I want to make the loading continuous, we say that let's have that additional loading till the point L. Say this is your loading downwards, then make same loading upwards to cancel the effect, such that the moment equation for this span is also constant moment equation, and after that point B has crossed, your new moment equation is also there. So this is the modification of UDL and UL by using the Macaulay's method. So we would say that you got a question that let's say that you got a reaction here is reaction R. Then after that you got a concentrated moment M. Then after that you got a UDL of you got a UDL of that this one W, and you also got that this UDL is also like this one. Then after that you got a uniformly varying load of W here W2. So if you got at any section at any X, here the moment is Mx. So if you write the moment equation that, say this is your length A, this is your length B, so we can write, and this is your length C. So we can write reaction R into X, then moment anti-clockwise moment m, it acts after point A. So we can write mx minus a power 0. Then we have that clockwise anti-clockwise w into this x. The value of loading is for this part. So it is after b. So we can write w into x minus b, and it acts for the entire section that after it reaches b, it is for the entire part after that point b. So we can write wx square by 2, wx square by 2. Then after that you have that uniformly varying load, and its centroid is here. So we can say it's after the point c. So we can write the area of that diagram, that's 1 by 2 loading intensity w1, and the length for which it acts, it is that equals to x minus c. So this part is your area of the loading, and um, it's valid for this part. Say this was your 1 by 2 loading into this was your area of the this was your area. So it's your loading p into you have to multiply it with the that that x by 3 where the centroid is acting. So we can write x minus c by 3. So we got the equation. So and here was moment mx equals to 0. In this question, that there's no need to modify the that udl and ul, no modification, no modification needed, because that udl was continuous till the point d, and uvl was also continuous point till the point b. So if you want to say, let's have some question. We can get the question that say here the reaction is reaction A, that we can calculate, that comes out to be 500 Newton. Then after that, at 1 meter from A, you have UDL of 400 Newton per meter, and the length here is 3 meter. Then after that, you got a reaction here, 1300. Point D, this is 2 meter, and this one is also 2 meter, and here is a point load of 600 Newton. So these reactions 500 and 1300, we got it from force equilibrium and moment equilibrium. You can solve for that. And then after that, we need to say what is the moment equation mx. But for that, since your loading is not continuous, we have to make the loading continuous. Let's say want to make the loading continuous. For that, let's say we copy that. We have to make the loading continuous. So we can do that. We can make the loading continuous. Let's say we have added UDL of this 400 kilonewton for this span, and similarly we have to subtract it. Say loading is acting upwards now. Here the arrow is upwards, loading is downwards. So we can say that let's cut a section at x. Say this is your section at x. We can write here the shear is Vx, and moment here is mx. We can write equation that 500 into x clockwise, then minus 400. It acts for length of, say the length total length is x, but the UDL is acting for this part, that 400 into your 400 into that x minus the length 1 meter, x minus 1 meter, and then you have to its centroid would be somewhere here at x minus 1. Then we can write wx square by 2, this one. So wx minus 1 whole square by 2. Then after that, you got vertical UDL of same that intensity. So we can write positive 400 into x minus from what point your upward UDL is acting. That means after you cross at that point 4 meter, then UDL is acting. So we can write x minus 4 whole square by 2, but it's that clockwise about that point x. Similarly, you have reaction 1300, that's also clockwise 1300 for length of x minus this 2 plus 3 plus 1, that's 6, that x minus 6. Then we have moment here mx anti-clockwise, so we can write that finally positive mx. So we got the equation that moment at x equals to this one. So we can say, let's make it now. Let's write that ei d2y by dx2, that equals to m at x, that equals to, let's say that 500 Newton is valid for the entire section. So we can write 500 into x. Then after that you apply oblique sign, so we can write 400 by 2 x minus 1 whole square. Then after that you have to write plus 400 x minus 4 whole square by 2. Then after that you have to write 1300 x minus 6. Then you have to integrate it one time. For the first time you integrate it, so we can get ei dy by dx, that equals to 500 x square by 2 plus constant c1. Then after that minus 200 and x minus 1 whole cube divided by 3. Then after that 200 x minus 4 positive, then means power 3 divided by 3. Then 1300 x minus 6 whole square by 2. Then after that you integrate one more time, you can get the value of delta, that's 500 x cubed by 6 plus c1x. So we can get the value of c1x plus some constant c2. Then we have minus 200 by 3 into x minus 1 whole power 4 by 4. Then we have 200 by 3 x minus 4 power 4 by 4. Then we have 1300 by 2 x minus 6 power 3 by 3. Then we say what are the boundary conditions that we have to impose. Say at the support A there would be delta 0, and at your support D delta is also 0. So we can use these two conditions, that delta is 0 at x equals to 0 and x equals to that 6 meter. We have delta equals to 0. So when we substitute that, delta is 0. So if you say that delta is 0 at x equals to 0, at x equals to 0 delta is 0. So we can get 0 equals to 0 plus c2. Then this is ignored, this is ignored, and this is ignored because negative, negative, negative. So we get c2 equals to 0. Similarly at x equals to 6 meter, your delta is 0. So you can write 0 equals to 500 by 6 into your 6 cube, then plus c1 into 6x. Then c2 is 0. That means after that you have to see whether the then after that we have to check whether these terms are valid or not. So we can write minus 200 by 3. Your value of x is 6. That means okay, it's valid. Power 4 divided by 4. Similarly, your 200 by 3, 6 minus 4, power 4 by 4. Similarly, this one, it becomes 0 because 6 minus 6, that is 0. So similarly, finally we get the value of c1 minus 1308.33. So we got the value of c1 equals to 1308.33. Then we have to get the the question was saying that get the value of delta at 5 meter from A. Say that deflection would be like somewhat this one. Then after that, to make the slope continuous, deflection would be somewhat this way. Say, but the thing is, let's say, but the loading is also there now. So let's say let's say that it would deflect downwards. Yeah, this would be possibility of that deflection curve. We don't have to draw the deflection curve. There is a possibility that at this point the load is acting downwards, so deflection would be downwards. And to here the theta is also same. The theta right and theta left should be same. Then because of these loadings, the deflection would be somewhere this way, and here it has to hog. Then there would be then here would be, the hogging curvature would be followed here. So it's saying that get the delta at 5 meter from A. So this was your 1 meter, 3 meter and 6 meter, then we have to get the delta at this 5 meter from A. 5 meter from A. So delta at 5 meter from A, we can write. Once we got that C1 equals 1308, we can write that. We can write. So we can write at x equals to 5 meter, your delta 5 becomes equals to that 500, 5 cubed by 6 plus your value of C1, that is minus 1300, 1308.33 into your 5 value, and this term is also valid for the 5 minus 1 power 4 divided by 4. Similarly, this term is also valid. 5 minus 4 power 4 divided by 4, and this term is not valid. You have to ignore that term. Ignore it, because 5 minus 6 is negative. You have to ignore this term, and you get the value of delta at 5 meter equals to minus 375 divided by EI. Let's say we have one more question, that uniformly varying load. So this is your simply support beam, and loading intensity is maximum at WL by 2. So since your moment equation changes, say if you want to say if you want to go up to the point X, you can say here the shear force is Vx and moment here is Mx, but the thing is up to the point, this point that moment equation is constant, because your because your loading is linearly varying. Then after that there is a change because the loading is decreasing, then so your moment equation would change. So to make the things clear, your Macaulay says modify the that uniformly varying load till the point B, so we can get a continuous moment equation. So to make the loading continuous, let's say we have to make the loading continuous. We would extend it, say this part up to this part, and we can join the two. So if you want to say how much loading we have added here, so by the symmetry we can say here it was W for the L by 2, so here the loading intensity should be 2W, and here the loading intensity, we have not added any load here. At the L by 2 we have not added any load. We can say loading intensity is variation is somewhat this one. So 2W and to 0. Similarly, you have to apply it in the opposite direction also. Say this was your 2W, and you have to apply such that at L by 2 you have to apply 0 intensity. So we can write here the value is 2W and loading intensity is 0, so the loading is upwards. So we can get the continuous equation that for the first part, that loading is continuous, that slope is continuous. So let's say the centroid is acting here, and for this part centroid is acting here, and initially we had to get the reactions for this case. You were having the reactions that it was W, it was L by 2. So the reaction is area of this part, area of the loading diagram, say 1 by 2, and WL 1 by 2 W into L and divide by 2, because reaction 1 and reaction 2 are same. So finally you get the reaction equals to WL by 4. Here the reaction was WL by 4, and the reaction here was WL by 4. So when you got the section at X, so we can write the moment equation that WL by 4 into X, and it was clockwise, and after that you had anti-clockwise, that 1 by 2. Say when you cut the section at any X and it is uniformly varying, say W dash here is, and it is X, we can write W dash, but the value of W dash is such that maximum intensity is w dash is such that maximum intensity is 2w for length L, and if you need it for length X, we can get the intensity that 2W X by L, and area of the curve, area of the diagram, which is half of perpendicular into base, and 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 it acts at X by 3 from the section X, so it acts at X by 3. So similarly, we can have for the upward reaction that it's clockwise, so we can write upwards 1 by 2, and similarly we can have 2W by L. But the thing is here, it's not L, it's varying in the it's varying in for the length L by 2 only. So 2W is varying from 0 to 2W in the length L by 2. So we can write in the length L by 2, but you need for only not X, you need for this part. Let's say the X value is somewhere here, and the loading intensity is this part W dash. Say the loading here is this one. Say loading here is W dash. Value of X is this part. Okay, and loading is acting downwards. Centroid is somewhere here, and you want to say that what is the value of this length on which that UVL is acting. UVL is acting, say total length was X, but it's acting for yeah, total length was X. So this value would be equals to X minus L by 2, because your length here from this part to this part, it's L by 2. So your loading is just for that total X minus L by 2. So we can say the area would be that, we can write area would be X minus L by 2. Once you got that, half of that 1 by 2 into your loading intensity. Loading intensity for L by 2, but you need for X minus L by 2. So this is your half of perpendicular. You have to multiply it with your that value of X. The value of X is also X minus L by 2. X minus L by 2. And the centroid here is acts at that X minus L by 2, and divided by 3, 1 by 3 of that. So this part is your 1 by 3rd of X minus L by 2. X minus L by 2. This is the centroid of that. So 1 by 3 X minus L by 2. 1 by 3 X minus L by 2. So we got this equation, and moment was also there, mx, that was anti-clockwise, mx equals to 0. Finally you shifted the mx to the opposite side. We can write mx equals to this value. Then you got equation. You got this equation. Now the calculations are very much. So we can now simplify this. So we can write that equals to EI d2y by dx2. So if we apply that oblique sign here, oblique sign and oblique sign that. If you want to simplify the values here, we can say this WL by 4x. This is minus 1 by 2. This is W x cubed by 3L. Wx cubed by 3L, and this one is your W into your 2W by L. Then after that you have X minus L by 2 for how much times? It's 3 times. So we can write X minus L by 2 cube, and you have 1 by 3. So we can write 2 by 3 that. This is your moment equation. So we can write EI d2y by dx2. So to get that for the slope, we have to integrate it. We can write EI theta equals to that yeah, that WL by 4 x square by 2 plus some constant C1. Then after that you have minus W x4 by 12L. Then we have WL by 3L x minus L by 2. See, we have to see, we have to increase the power by 1. So we can write x power 4 divided by 4. So similarly, EI delta equals to WL by 4 x cubed by 6 plus C1x plus C2 minus WX power 5 by 60L and then 2W by 3L 2W by 12 2W by 12 12 x minus L by 2 power 5 divided by 5 such that it becomes 60. So similarly, then you apply the boundary conditions. Now for this case, you apply the boundary conditions that now if you apply the boundary conditions, say at x equals to 0, your delta is 0. So if your delta is 0, that means C2 you would get C2 equals to 0. Then after that you had at x equals to L, you say delta is also 0. Then you substitute the value here, and you at L every term is valid, and at x equals to 0 these terms are ignored at x equals to 0. So you get the value at x equals to L, that delta equals that C1 would be some value of minus 5 upon 192 WL cube. The calculation that practice is all about you, that civil engineering is that how much practice you make yourself, you do. So it's all about that, how strong your concepts are and how much problems you solve by yourself. So when you get the value of C1, you got the value of C1, we can say, the question was saying that get the value of, say, deflection would be somewhat this one, get the value of delta max. So delta max, by symmetry we can say, delta max is at mid, that means at L by 2. So we can write at L by 2 at x equals to L by 2, delta is your delta mid or delta max. You can get the value of delta max by substituting the value of that constant C1. That C1 was this one. So if we substitute the value of say we substitute the value here, say we are substituting the value here, EI delta maximum delta mid equals to at x equals to L by 2. We can substitute the values WL into L by 2, and you are 24 plus C1 minus 5 by 192 WL cube into L by 2. Then this term, this is valid. This term is valid because, is it valid? WX power 5. Yeah, because it's UDL, I think. How we got this WX cube by L? Yeah, it was because of that uniformly varying load. Yeah, correct. So we can say this is also valid because it does not have any x minus something. So it's valid. We can write x WL to the power 5 by 2 to the power 5 and 60L. And this one is your ignored because your L, L by 2 minus L by 2, that is 0. So this one is 0. We can say this one becomes 0, not ignored because your L by 2 L minus L by 2 is 0. So we can't ignore this. So finally we get the delta mid that equals to minus WL to the power 4 by 120 EI. Negative means deflection is downwards. So this is one of your standard results, that deflection at mid equals to WL to the power 4 120 EI. So let's say you have a loading configuration loading configuration of that that this is your support B and support A. Loading concentrated moment M1, concentrated moment M2, and loading W1 here. So this is your A, this is B, this is C, and this is L. You want to say what is the moment equation? Say if you cut the section here, you can write here mx. So we can write, say the reaction here is A, we can write A into x minus that this moment is also clockwise, we can write m1, but it acts at, but moment 1 acts at, your moment 1 acts at x minus A, so we have to show the power also that x power 0. Similarly, you have the anti-clockwise moment about the point B because of the W1, so it acts at W minus that x minus B. Similarly, you have that anti-clockwise moment, so we can write minus M2, but it acts at x minus C, so, and we show that power 0, and after that you have minus moment at x equals to 0. Finally, you got the moment equation, and you can solve that. So not let's say that let's say you want to say equals to 0, that equals to ei d2y by dx2. So if you want to say what is the ei dy by dx, you can write by integrating it once, we can write ax squared by 2 plus c1, then we apply those oblique signs, so we can write m1 x minus a power 1 by 1 divided by 1, then we write x minus b power 1, this was already 1, we can write x minus b whole square by 2 divided by 2. Similarly, eiy, that equals to ax cube by 3 plus c1x plus c2, then m1 by 1 x minus a, then squared by 2, then you have w1 by 2 x minus b whole cube by 3, then minus 1 minus m2 x minus c powers 2 by 2. This is how we can solve if the concentrated moments would be given some values, and you can solve it for the deflection and slope. Let's say the before that we had one question. Now we are changing the loading such that now maximum is here and maximum is here, then it goes to 0 at the L by 2, and it goes to 0 at L by 2. So we can clearly see that your moment equation would change. Definitely, say it's your L by 2, so your reaction becomes WL by 4. Reaction becomes WL by 4. Let's say you want to say what is the let's cut the section at x. Here the moment is mx, but the moment equation is varying. So to make the moment equation continuous, we can say let's apply our moments that let's apply loading such that the loading is continuous. Let's say we are applying a loading that if you apply this moment, that not moment, this loading, extra loading, you have to also subtract it. Let's say you applied it in such a way that loading here was maximum, so it should be somewhat this one. Let's say the loading here you applied W because it was 0 here and it was 0 here. To make it as a UDL, you applied a loading of W downward direction, so you have to apply loading of W down upwards, and at this point you applied loading of 0, so you have to apply here 0, then it's all loading upwards. But the thing is, it again became that moment equation again became discontinuous. Now we already saw that for this loading, we said that we extend it such that it becomes 2W, and then applied that upwards that 2W. Similarly, we can now apply that. We can now extend this one also. So we are applying that here 2w, and the loading here is upwards 2w. Similarly, we have to subtract it. So we can say here we are applying 2w, and here we are applying 0. So it's acting downwards. Now we can see that the loading became now continuous. Now the loading became continuous. So we say that now you got finally you got a UDL of W for the entire span, and you got a uniformly varying load of 2W at the end span and 0 at the mid span at the ends, and you got 2W and 0 at the L/2, and similarly you got one more uniformly varying load. It's acting upwards for the entire span, whose maximum is 2W, and you got this one downwards, and UDL is also downwards. So the reaction, we know that it's equals to WL/4. So when we cut the section at x, we can get the moment equation that we can write the moment equation that WL/4 minus WX squared by 2. Then after that you have the centroid of this one and centroid of this one. So this one is your positive moment about that section x when we cut the section at any x. So moment at x, we can say the loading intensity is as that we can write positive area of the triangle that's clockwise 1 by 2 into loading intensity is W dash, such that it becomes equals to 2W per length L, but I need for length x. This is your perpendicular, that's your loading intensity. Then you have to multiply it with your length x. Then after that it acts at the centroid, that x by 3 from that section x. Then similarly for this loading, we already saw that how to get that particular length, that this length x. We say that total length is x. Here the intensity is W dash, and it acts only for this length x minus this length is x minus L by 2. So we can write that minus times anti-clockwise moment of area of the triangle is 1 by 2 into W dash. W dash is 2W per change in length is change length L by 2. It changes 2W to 0 in length L by 2. So we can write we need for how much length? We need for the intensity at x. We need for this length, that x minus L by 2. And we got the loading intensity W dash. You have to multiply it with the length you need it. We need for that base equals to x minus L by 2, and similarly it acts at x minus L by 2 and divided by 3, 1/3 of that base. So we have that moment at x. So finally we got that moment at x equals to EI d2 y by dx2. Now we can apply the oblique sinus also. Say this one is your oblique sine, this one, and this one. So finally we can say, now if you want to say EI dy by dx equals to, let's say you can do you say integrated wx squared by 2 plus some constant c1, and after that you had wx cube by 6l. So when you integrate it, you get wx cube x power 4 by 24 into l. Similarly for this case, this one and this one goes, and 2 power would go upwards, 2 by l. Then you had w, and you had 3 also here. Then you had 1 2 3 times of this one. So integrating it, you can get 4 times of this one divided by 4. Similarly you can get EI delta equals to minus wx power 3 by 6 plus c1x plus c2. Then we can get that wx power 5 divided by 24 into 5, it is 120l. Then we have positive that 2 by 3 of w by l. Then we have x minus L by 4, x minus L by 2 power 5 divided by 5. Yeah. and also that 4 was also there, 12. Finally it becomes 60, 12 into 5. So by applying the boundary conditions now, we can say at delta at x equals to 0, your theta, your delta is 0. At x equals to 0, delta is 0, and x equals to L, delta is also L. Delta is also 0. So by substituting the values, then we can get that C2 comes out to be 0. When we say that x equals to 0, your it becomes 0 plus 0 plus C2 plus that 0 plus that ignored, so C2 becomes 0. Similarly, at x equals to L, delta becomes 0. When you substitute the value of x equals to L, you got the value as this one, C1 into L, and plus this term is also included. We can write WL to the power 5 divided by 1 to the power 120L, and this part L minus L by 2 is not ignored, because it has that L minus L by 2, that's positive, so we can't ignore that. So we can write 1 by 30 W by L, L minus L by 2 power 5. So finally we can get the value of C1, that comes out to be equals to minus WL cube by 64 minus WL cube by 64. So want to say what is the delta maximum. So from the figure we can say for this loading, you got this loading, we can say delta maximum would be somewhere at the mid. Say delta maximum at L by 2, we can say at x, we can say now apply the condition that at x equals to L by 2, we can have delta maximum. Then substitute the value of x in this equation. Let's say this is your equation. We can substitute value of x equals to L by 2 whole cube, then L by 2, this was your 0, then here L by 2 power 5. Similarly here L by 2, this is 0 because L by 2 minus L by 2, this is 0. Then you get the value as delta maximum comes out to be equals to minus 3 by 640 WL to the power 4 by EI. See, we yeah, that would be doing in the next part. That we could also solve that by superposition, that we have not studied till now, so that superposition method, so we can skip it for the later part. So I think we should end the class because we got two methods. That first one is your double integration, and after that advancement of double integration, that is your Macaulay's method. So we solved a lot of questions on both the methods. Now after that we'll be dealing with the superposition method in the next lecture. Hope you enjoyed the lecture. The calculations are very lengthy because it includes integration, and you need differentiation and integration of those terms, and it becomes lengthy calculation. That I hope you understood the problems and try to solve by yourselves also. And thank you for watching our lecture on concrete path.